The thing I want to talk about is a collaboration which is done with my friends in Oxford. Andreas Brown, who is in the audience, Colin Brody, who is a student in Oxford, who did great work on this, and Andre Lucas. It's hopefully appearing this week or the latest next week, so we are almost finished. Okay, let me start with the motivation. The work was motivated by two questions, and my talk will also be about these two parts, which are related to one another. So first of all, of course, the heterotic spectral cover F-theory duality has been worked out since the very early days of F-theory, in particular in the Friedman-Morgan-Witten paper and a lot of papers that followed. So we asked, what about bundles that don't have a spectral cover description, or at least not a useful spectral cover description? What are their duals? And secondly, and as I will show relatedly, often we have NS5 branes in heterotic models, which, as you all know, and as we will probably hear a lot of talks about, this you get then E-strings or M-string theories from these NS5 branes, relations to superconform field theories, and so on. And we want to ask, how do these NS5 branes or M5 branes on the heterotic side map onto the F-theory description? So here's the outline of my talk. I will very, very briefly review the heterotic F-theory duality, and then I have these two parts. First, where I discuss F-theory duals of line bundles. So line bundle models are one particular example of models that do not have a spectral cover description. And I will match the big three, the anomalies, the stability, and the matter. And the second part will be about the NS5 branes, where we will be matching the NS5 brane spectra. First of all, if you have a bunch of NS5 branes, and then we will look at what happens if you stack them or intersect them transversely. Okay, so the very brief recap is we consider F-theory on a Calabi-Yau n-fold Yn, so Y will always be the F-theory Calabi-Yau, and essentially in this talk I will only be talking about n equals 4. So Calabi-Yau 4-fold, you have a three-dimensional base, an elliptic fibration, the thing itself is K3 fibered. I will call this P1 here the F-theory P1, because this is sort of the difference between the heterotic base and the F-theory base. So now if you map this to M-theory, sort of the north and the south pole become the boundaries of the Rojava-Witten interval. I will draw them like the east and the west pole here, because it makes it easier to draw. Then you can take the stable degeneration limit of this thing, which essentially means that your P1 degenerates into two P1s, which at a point, and the east and the west pole go here and here. And this is a interesting limit in which you have to sort of send volumes, the volume of the F-theory P1 to 0, and the volume of the fiber and the base, both to infinity, with the volume of the larger than the volume of the fiber. This leads to this degeneration of the manifold, like so. And then from there you can go to the heterotic by just, the end of the world branes, let's say at the end of the Rojava-Witten interval, just go into the E8 bundles, and you get then the elliptically fibered Calabi-Yau 3-fold on the heterotic side over the two-dimensional base. Or if you come from this side, sort of you have these east and the west pole where you have the E8 sitting, this point just, so over the intersection of these two P1s which touch at this point, you get then the heterotic manifold. This is how the duality is set up in the F-theory and the heterotic. So now we can consider two types of NS5 branes, which we call horizontal NS5 branes and vertical NS5 branes. The horizontal ones essentially wrap a curve in the base and are points in here, which means then if you do the M-theory Rojava-Witten picture, it still wraps a curve in the base. There's a point in the interval and a point on the T2. And these are mapped to the geometry of the Calabi-Yau 3-fold. In particular, they're mapped to blow-ups in the base along the curve that's wrapped by the NS5 brane. There are also vertical NS5 branes, which means they are point here, and they wrap the T2. So they go to point here in the T2. And now in the type 2 limit, of course, where this torus goes away, these are just T3 branes. We will focus on these ones because the vertical ones are very well understood, and there's not much new to be said that hasn't been said already. But here, this question of how we geometrize these NS5 branes in the dual F-theory picture is the main part of what we want to discuss here. Okay, so the first part now, as I said, will be about matching line bundle models, including NS5 branes, to the F-theory side. And okay, so as I said, in the original way you construct, or the usual way in which you construct gauge groups in F-theory is you take the elliptic vibration in codimension 1, engineer an ADE singularity, and this gives the gauge group. In Heterotic, you start with an E8 times E8 bundle, and you choose the structure group of your, you start with an E8 times E8 gauge group, and you choose the bundle such that the structure group of this bundle is the commutant with the gauge group you actually want to engineer within E8 times E8. So if you had a spectral cover construction, what happens is that the heterotic bundle sort of maps onto F and G such that precisely you get the commutant in here. So if you have an E8 bundle, the gauge group will be trivial, and F and G will have vanishing order 0, 0. And in other cases, I mean, it just maps over in this way. So line bundles, as I said in the beginning of my motivation, do not have a very useful spectral cover description. We take V to be just the sum of line bundles, and the spectral sheet of these things are trivial, so all the information is in the spectral sheaf, and this is not a description which we want to use. What are the duals, or how can we describe the duals in this case? So well, we start with an E8 times E8 singularity, and rather than in the spectral cover description taking the structure group and mapping it onto F and G, you put the full E8 times E8 singularity into F-theory, and then you break with G4 form flux to the gauge group, which is also the gauge group you break to with the heterotic bundle. What this means is you have two E8 gut surfaces in your fourfold. Each is diffeomorphic to the heterotic base B2, and you construct now a four-form flux G4 over this such that you get the breaking which you get in heterotic. So throughout my talk, I will denote stuff that goes into the fiber curve with a 0, and the other stuff in the base with the I. So every time you see a 0, you should think fiber. And so I can expand my V, which is a sum of line bundles, in terms of these flux integers K, A, I, which are the first Chern class of the line bundle we are specifying in H11 directions. So we want to apply the standard heterotic F-theory duality, and this forces us to put flux that is flat on the fiber, which means that, as I said, the 0 is the fiber direction, so K0A has to be 0 for all the line bundles. What that means is that all line bundles can be described as pullbacks from the base. In type 2b, what this maps to is just flux on the two E8 brane stacks, which are where the gut surface is essentially the heterotic base. And since the bundles are the pullbacks from the base, you sort of get this match. Okay, so now, as I said, I want to match three anomalies, spectrum, and bundle stability. So let's start with the anomalies. What you have to solve on the heterotic side are the Bianchi identities, which tell you that the second Chern characters, the difference of the second Chern characters, has to be an effective class, and this effective class is essentially the class that's wrapped by the NS5 brane. You can rewrite this due to the flatness in the bundle. In the T2 direction, you can rewrite this like so. And the first thing you note is that since K0, there is a part which goes into the direction that can only be cancelled by K0, but we had to set it to 0 in order to apply the heterotic F-theory duality. And this means that necessarily you do have horizontal NS5 branes always in the picture when you construct this duality, and it's always wrapping a curve in this class. And the rest of the flux you can choose to satisfy the leftover Bianchi identities. On the F-theory, you have the standard tadpole cancellation condition, which looks like this. And 3 is the number of D3 branes. As I said, we don't want these D3 branes, which would be the vertical ones. the vertical NS5 branes, you can include them, but as I said, it just goes through everything. So let me just, for simplicity, set them to 0 here. They just go along for the ride everywhere. Then, as I said, this part here is the flux. So the KI are the flux integers. So this is the flux on the 2E8 branes, and this is mapped onto the 4-form flux here. So this part goes here. So then the question is this here equal to the chi over 24? So this is the thing we have to match in order to match the anomaly conditions on both sides. And well, of course it is. You can use the projections to compute the Euler number of the fourfold in terms of the Euler number of the base, or in terms of the Chern classes of the base rather. And if you do this, if you use the sections, first of all, you have a projection which projects to the F3 base, and then you have a vibration, so you also have something that goes into the heterotic base, and you can write this in terms of the Chern classes of these bases, like so. So this means that this part has to be equal to this part. And now if I subtract this 10C1 squared from here, I just get that C2 plus C1 here be equal to this expression. And in fact, this is true for all our bases. This is just the Euler number, or the alternating sum of the HI zeros, and for the bases that lead to a Calabi-Yau, these are necessarily, so this is the first diagonal of the Hodge diamond, these are necessarily 1, 0, 0, 0, because if they weren't, you could pull them back to the forms on the Calabi-Yau, and your Calabi-Yau would have an H10 or an H20. So this is just 1 in both cases, and this is how the mat comes about. Secondly, stability. Well, on the heterotic side, you just have to solve the Hermitian-Young-Mills equation, and the integrability condition for that is the Donaldson-Uhlenbeck-Yau condition, which means that you have to satisfy J which V equals 0, where J is the Kähler form, and T are the Kähler parameters. D is the triple intersection number. So now you can insert all these intersections, so you don't have 3 intersections in the base, because the base is 2-dimensional. K0A is 0 because you want it to be flat along the fiber. You do all the math, and what you find is an expression like this, where the first part is essentially just the Kähler form on the base wedged up with the flux, and the second part is, you see the zeros here, so this is the volume of the T2. Now, in the limit we are considering, I remind you, is this stable degeneration limit, where both of these go to infinity, but the volume of the T2 is much smaller than the volume of the base. So in this limit, this extra term goes away, and we're just left with this term. We can divide by T0, which is non-zero. So we get an expression like this. And this is, of course, just the F-theory stability condition of a flux 7 brane, where you integrate over the 7 brane, the flux. But as I said before, this gut surface S here is diffeomorphic to the heterotic base. So these two conditions are again the same. Thirdly, the spectrum. Well, the simpler part is first the chiral spectrum. You can compute the chiral index of the bundle, which is given by Hirzebruch-Riemann-Roch character times the Todd class. It's this expression. And now you can insert again the fact that you don't have a K0 and that Dijk is 0 and so on. And this means that none of the terms survives in here actually. So chi of the line bundles is always 0. So you can never have a F3 dual of line bundle models that is chiral, which is of course from phenomenological point of view is kind of disappointing, but this is really just what you have to do if you want the bundle to be flat on the fiber. But we can do more. We can match the entire homology groups, and this essentially just becomes an exercise in algebraic geometry. You use the Lie spectral sequence to compute the homology groups, and then you check, I mean, all the bundles are pullbacks from the base, so you can track these through the high direct images of the spectral sequence. You can use the absence of sections for stable bundles, so H0 and H3 are 0 here. Furthermore, H2 here is 0 for effective bases, so that NR is really just H1 of B2V and NR star. So number of particles in representation R and R star is just given by the first cohomology dimension of this thing. For F-theory, this has been done as Timo explained briefly, you can do this locally on the twisted theory for flux 7 brane, and done by B.C. Heckman-Waffer and by Donagi-Weinhold, and you get, in general, you get these expressions where, again, H0 doesn't appear. This is 0 for an effective base, so we are just left with little 2 ones here, and again, the 2 things match over. And of course, so you could have sort of, if you know this, you could more or less have guessed this from this being 0 and not having H0 and H3. And these 2 then have the same. Okay, so this is the match for the spectrum, the anomaly conditions, and the stability. So these 2 things carry over beautifully. So now let me come to the second part, which are NS5 branes. So on the NS5 brane spectra, well, on the heterotic side, to compute the number of chirals and vectors, I do neglect the E8s here because they are just always there. We don't do anything with them. So I don't want to, I just don't list them here in the formula. So you get moduli-wise, you get the usual geometric moduli, and then each NS5 brane contributes, each NS5 brane on genus G curve contributes 1 chiral and the G vectors, as was worked out here. And then you also get the deformation moduli of the 5 brane. So these are the 2 expressions for the chirals and vectors you get from the NS5 branes. On F-theory, this has been worked out by Maury, Lust, and Thomas. And it's just a combination of the Hodge numbers for the chirals here and the vectors here. Here you can use the fact that these are the number of extra sections you have. And so we just consider simple Weierstrass models with 1 section, the holomorphic 0 section. So this essentially goes away, and the number of vectors is just H1 of BF3. So this has to be equal to the sum of the genera here, and this expression has to be equal to the number of chiral multiplets here. Well, this is not so hard to show. You can use the Künnes formula and the fact that H10 over P2 is 0, over P2 is 0, so then this means that this is 0. Before the blow up, the Euler number is just 2 plus 2 times H11 minus H21. So this 2 is, as I said, you have on the first diagonal, you always have a 1, 0, 0. Now if you do a blow up along a genus G curve, the Euler number is changed by 2 minus 2G. But we know that also H11 is changed by 1. So this means, by factoring out this 2, this means H11 is changed by 1, and H21 is changed by G. And then this is precisely the formula we had up here. Well, to show this, there's a little bit more work, and we have to make a technical assumption that we only wrap NS5 branes on curves that do intersect the anticanonical bundle of the base. We discussed situations in the there will be a discussion of what goes wrong if you relax this assumption, but for now let me assume it because I don't have time to explain. This is a very subtle, it's interesting, but it's very subtle. So well, you can use from the vectors, you can use that H21 is just the sum over G. So you could just get the sum over G here. And then on the left-hand side, you can use that the number of deformations is kb.c minus 1 plus the genus. In total, we have to blow up 12 kb. This gives this 12c1. The sum of the ones gives the number of NS5 branes. And the sum of the genera remains and cancels this term. So this is how you match the chirals. And we find thus that the vectors and the chirals match on the heterotic and on the F-theory side. So let me now briefly explain how we do the blow-ups in the toric description in order to explain later then how we describe the intersecting and coincident NS5 branes. So we have a 4-6 12 point in codimension 2 where the E8 singularity intersects the I1 locus. And you can blow this up torically, which gives a bunch of P1s, or you can use NEF partitions to get more general degree N curves on which you can then wrap the NS5 branes. So this is a simple example of P2 times P1. So we have the P2 here in the XY plane, the P1 in the Z plane, and then in the extra planes we have the Weierstrass torus. So these are the coordinates of the P2, these are the coordinates of the P1, and these are the coordinates of the T2. And you just put them together like this, and you get something that's P2 times P1 times T2. So now if you want to put NS5 branes, as I said, we blow up. In the beginning we have 18 intersections here and 18 intersections here, say. Now I blow up, and this means I put one of these intersections as corresponds to P1, which goes into the Rojava-Witten interval. And I do this blow up, for example, over E3. This is now above here. Get to a second blow up below. This puts something from the other brane into the bulk, and I can do this repeatedly until I've blown up 36 times, which is 12 kb. For this case, I get 36 P1s and nothing in the 2 E8s. So now I have 36 NS5 branes that wrap P1s, and they are all separated. I can also do this for, as I said, this will only give me P1s. If I want an F partition, I can use a trick where I sort of take n of these P1s and fuse them into a degree n curve by introducing another coordinate here, another equation, and putting a minus n in the right spot to give the degree n curve. This gives me then a singularity I can blow up, and I get then a complete intersection or an F partition that describes this degree n curve. So now what can happen? So now let me look at intersecting these things. So now we have 36 or whatever n different NS5 branes, and now I want to see what happens if they intersect transversely or if you stack them. So let's look at the transverse intersection first in M theory. Intersecting, that means you intersect them here and you put them at the same position in the Witten interval, which in the F theory is sort of you just get one dimension more. So we have the two gut surface or the two E8 stacks, and then you have the P1 direction, and you have this transversal intersection. Now we can, as I said, we can use nav partitions to deform them to a degree n curve. There's one way of getting rid of it. Or you can sort of take the points and move them apart in the Rojava-Witten interval, which means now that these two things don't intersect anymore. For coincident branes, this also means you have to stack them here and in the Rojava-Witten interval. So here you get a stack of NS5 branes in the F-theory picture. Again, you can deform this to a degree 3 curve or so, which looks like this in the F-theory. Or you can resolve it. By resolving, you can either pull them apart here to something like this, or you can just pull them apart in the Rojava-Witten interval and leave this part invariant to something like this, or of course you can do both to arrive at something like that. In the dual M theory, in the dual F theory, this just means that you take all these stacked ones and you pull them apart. So this begs two questions. First of all, if I compute the spectrum, the U1s, as I said, are counted by the genera of the curve on which the MS5 branes are wrapped. So this is U1 of the to the G deformed, where the G deformed is the genus of the deformed curve. And here I get just n times G if I resolve this completely, where G are the genera of these curves. And these in general might be very, very different. So the question is, what is this thing in the middle? And of course, so this thing in the middle in 4 dimensions is not very easily described. It's as I said, you have these tensionless strings and all these things. But instead of describing it in 4D, we can use this very nice paper by Hans and Dave and others 1 year ago, where they matched this in 3D. And there it's just a normal field theory, and we just find this SUN and these two U1s, and everything works perfectly. The second question is, we have all these different things here, and just this one diagram in F theory. So where does all this information go, whether it's separated in the bulk or in the Rojava-Witten interval? This is just a separation here. So where's this information in F theory? Well, to make an example, I consider P1 times P1 base, and I blow this up over one of the P1 rays and over the other one. So somewhere in my toric description, I have something like this, where I have the U1 and epsilons above, this V1 and blow up rho's above. And now from there, I can, for example, delete this epsilon 1 here, this vertex, which gives then something like this, and this leads then to the coincident brane picture. So this would be sort of going from here to here. Or I can delete a one phase in this diagram. So this thing here, this leads to transversely intersecting. So now these two can intersect. So now I get a transversely intersecting of the epsilons with the rho's. Or I can have a situation where I have a bunch of stuff blown up over U1, a bunch of stuff blown up V1, and I get something like this. I choose a triangulation. And now, of course, I can flop in this triangulation. And depending on the flop, so the triangulation now encodes how these things are ordered in the Hojava-Witten interval. Because, so now, so if I do this, I see that this U1 is connected to these two V1s, then this V1 is connected to a U1, this U1 is connected to two V1s, and we get this picture above here. So this means that the position in the bulk is mapped into the relation of the diagram. And of course I can now combine this also by removing some of the things, and I get some transversely intersecting on top of that and so on. So this is how we map the information from the interval onto the toric description in F-theory. Okay, let me conclude. Well, I did two things. I discussed heterotic F-theory duality, line bundles, and NS5 branes. As I pointed out, the gauge group, in this case, if you don't have a cover description, you break it with flux rather than geometry. The thing that it's flat on the fiber led to two important points. First of all, you cannot build chiral models with that. Secondly, you need horizontal NS5 branes because the K naught being 0 means that you have a part in the heterotic anomalies which cannot be cancelled other than by wrapping NS5 branes on the corresponding curve class. We matched the tadpole, the spectra, and the stability using standard techniques in algebraic geometry. And in the second part, the NS5 branes, we described them by toric geometry or NF partitions. We matched the spectrum we get in the F-theory picture. We also matched it, as I said, so this was for the separate ones, for the coincident or intersecting ones. We also matched it in the paper. I haven't discussed this here because I didn't have time. But we did this using Lucas et al. And we explained how to see the M5 brane position in the bulk and how this maps to the triangulation of the toric diagram. Okay, thank you.
Okay, thanks a lot. Any questions? Yeah, Jonathan.
Sorry, can you say more about the theory you got from the transversely intersecting M5 branes? So you said SUN plus CFT question mark?
Yeah, that's a good point. As I said, we didn't try to match it in 4 dimensions because we didn't really. I mean, as I said, you get these extra contributions from the tangential strings. So in dimensions, we can use M theory on the Calabi-Yau fourfold with the surface of singularities. And there, it was worked out by Lucas et al. That you just get a standard field theory, and this has an SUN gauge group. I don't know in 4 dimensions. I don't know what the theory here is here.
How much supersymmetry does it have? 8 real supercharges or 4?
It should be n equals 1 in 4D.
Oh, so then why isn't it E string on a 4 punctured sphere?
Sorry?
String on 4 punctured sphere?
Maybe it is. We haven't tried to match it in 4 dimensions. We only looked at the match in 3 dimensions.
Oh, but come on, it's got to be that. You have 2 things cutting like this. It's 2 P1s, and then you glue it together, so it looks like a sphere with 4 legs coming out.
Yeah.
So that's
yeah. Maybe that's the description. Yeah. We haven't tried to work it out.
Okay.
Yeah, so maybe you said this, but I didn't quite get it. So from the point of view of the geometry on the F-theory side, you do these blow-ups so that you're sort of forcing an E8 on the 2 sections. And then you put in fluxes to break down the E8. So which flux breakings did you look at? I mean, did you look at specific just to the U1 to some power, or you also looked at various other groups you can get when you turn on the fluxes?
No, so we only looked at, in this part, we only looked at the line bundle models. These are the ones that don't have a spectral cover description. Of course, you get think of pairing it with an SUN bundle which has a spectral cover description, then you would do the usual story where you just break part of it with the SUN, and then you can put another U1 bundles. I don't know what about non-abelian bundles, SUN bundles also, that do not have a spectral cover description.
Right, that's what I was asking about. So you didn't look necessarily at bundles that don't have a spectral cover description for other gauges.
Exactly. So we only looked at in this work we only looked at U1s, at U1 to the N bundles that don't have a spectral cover description.
Okay, thanks.
I mean, maybe you could study the other ones. I'm sorry. Maybe you could study the other ones by taking this U1 to the N bundle and go away from the split locus where this is fused into an SUN bundle. That still doesn't have a spectral cover description. That's a good point, but we haven't looked at it.
Okay, if not, let's thank the speaker and the speakers of the morning session. Thank you. So for lunch, just follow the local.